Hello everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture, we derived the area ratio Mach number relation. So from that area ratio Mach number relation, we came to know that for a given area ratio, we'll have only one supersonic Mach number. So as long as I change the area ratio, I can get the different Mach number at the nozzle exit. Okay. So what we are going to see in this today's lecture is that we are going to see discuss something about nozzle operating conditions. Okay, so what is this nozzle operating condition? Why does this is important? And what is a nozzle operating condition for a conversion nozzle? What is the nozzle operating conditions for a conversion diversion nozzle and all? We are going to discuss in today's lecture. Okay, so we know flow through your nozzle is, we are treating it as an isentropic. So we have the isentropic relation, that is P naught by P is equal to 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. Okay, so we have already seen for the choking condition. Okay, so what is the meaning of choking condition? To get m is equal to 1 at the throat location, we'll have P naught by P is equal to m is equal to 1. That will be 1 plus gamma minus 1 by 2 whole power gamma by gamma minus 1. So that will be gamma plus 1 by 2 whole power gamma by gamma minus 1. So in this, if I'm going to substitute for the normal air, we have gamma is equal to 1.4. If I'm going to substitute gamma is equal to 1.4, I'll get P naught by P is equal to 1.893. So what is the meaning of this P naught by P is equal to 1.893 for the choked nozzle is that if I'm going to give my total pressure P naught, so usually what is that input we are giving to your nozzle? We are giving pressure. That pressure is converted into kinetic energy in the nozzle. So if the total pressure of my inlet of my nozzle is 1.893 times of my back pressure. So what is the meaning of back pressure? Basically, it is the pressure of your environment to which your nozzle is injecting its flow. Okay. So if I'm going to give P naught is equal to 1.893 times of my back pressure, you will have the choking condition. Okay. Choking condition means in the conversion diversion nozzle or in the conversion nozzle. For your conversion nozzle, you will have at the exit m is equal to 1. For the conversion diversion nozzle, at the throat location, you will have m is equal to 1. This is the choking condition. So as long as my total pressure is greater than this, I'll have m is equal to 1 at the exit of my conversion nozzle or m is equal to 1 at the throat location of my nozzle. Okay. Now, if I'm going to increase this P naught, what will happen is that, let's first take a conversion nozzle. Okay. So your conversion nozzle, it is, if I'm going to give anything more than this P naught by P naught is equal to 0.893 times of your back pressure, you will have m is equal to 1. But what will happen is that at the exit location, you will have some pressure PE. Let's say that is the exit pressure of my nozzle will be greater than PB. Okay. So if I'm going to give more than, what is that meaning? A conversion nozzle is capable of fully expanding a flow which is having P naught of 1.893 times of my PB. Okay. If I'm going to give less than this 1.89 times of your PB, what will happen is that your nozzle is going to produce a subsonic flow. Your conversion nozzle will produce subsonic flow. If I'm going to give exact 1.893 times of your PB, at the exit, you will have m is equal to 1 and your PE will be equal to PB. Okay, so this PE is equal to PB and for your subsonic flow, for always, you will have PE is equal to PB. That is, what does it mean? All the given pressure energy is converted into kinetic energy. So you will have at the exit, your exit pressure will be equal to back pressure. This operating condition, what we call it as the correctly expanded case or design condition for a conversion nozzle. Okay. Similarly, if I'm going to give a pressure anything more than this 1.893 times of your back pressure for a conversion nozzle, what will happen? It won't be able to expand. It is capable of only expanding this 1.893 times of your back pressure. If I'm going to give, let's say, my P naught is 2 times of PB, means at the exit, you will have PE greater than PB. Okay, so what will happen? Your pressure is more than your back pressure. So in order to attain the equilibrium with your surrounding, what will happen is that you will have the formation of waves. Okay, you have M is equal to 1 achieved at the throat location. We already know in a supersonic flow, any change of state will always occurs through a certain type of wave. Okay, so here what will happen is that since your pressure is more than your back pressure, you have to reduce your pressure in order to attain the equilibrium. So what happens is that you will have the expansion fan formation at the nozzle exit. Okay, so what will happen once expansion fan forms means your flow pressure will be reduced. So there it will try to attain the equilibrium. Okay, so this condition of operating in the off design condition, what we call it as the nozzle operating condition. So if I want to get a maximum performance out of my nozzle is that you have to operate your nozzle at the design condition. For the conversion nozzle, you will have two operating conditions. One is a correctly expanded case, another one is the under expanded case. Okay, correctly expanded case is when your P naught is equal to 1.893 times of your back pressure. Okay, if you are going to give more than that, we can say your nozzle is operating under expanded case. Okay, this is for the conversion nozzle. If I am going to take a conversion diversion nozzle, okay, let's take a conversion diversion nozzle. For a conversion diversion nozzle, we already stated once I fix my area ratio, it will produce only one Mach number. Okay, similarly, a conversion diversion nozzle also is capable of expanding only one total pressure to correctly expanded case. If I'm going to give less than the total pressure or greater than the total pressure, what will happen is that you will have the off design conditions. Okay, so let's say for example, I have designed a conversion diversion nozzle for M is equal to 2. So if I'm going to substitute M is equal to 2 in my this equation, what I'll have is that I'll have this P naught by P is equal to 7.82 times of P, or you can say P naught is equal to 7.82 times of PB. Okay, so what is that meaning is that if I have a conversion diversion nozzle which is designed for Mach number 2, when it is going to operate under correctly expanded case or design case is that if my P naught is 7.82 times of my back pressure. So only for that 7.82, what we will have is that at the throat location, you will have P is equal to PB. This is what we call it as the correctly expanded case or design case. What is the meaning of correctly expanded case or design case is that all the pressure you have given to the nozzle is converted into kinetic energy. So by the time your flow reaching your exit, the pressure of your exit is equal to your back pressure. That is, whatever the pressure you are giving excessive of your atmospheric pressure to the nozzle, that all excessive pressure is converted into kinetic energy such that by the time it reaches the throat location, we have P is equal to PB. This is what we call it as the correctly expanded case. Okay, so instead of instead of giving P naught is equal to 7.82 times of PB, what happens if I'm going to give P naught by P, or P naught is equal to, let's say, 8 times of PB, 9 times of PB, or 10 times of PB? What is that meaning is that your nozzle is only capable of expanding 7.82 times of your back pressure. If I'm going to give more than that means it is not able to expand. So you will have still some unused pressure energy will be available at the nozzle exit. So you will have your PB or PE will be greater than PA or back pressure PB. Okay, so what does that mean? You are not operating your nozzle, you are under correctly expanded case if you are having PE is equal to PB. So now you could ask, what happens? Why do I bother about what happens if my exit pressure is greater than my PB? Is that we have, let's say, thrust equation F is equal to m dot A into 1 plus F UE minus UA plus A into P minus PA. Okay, so this is our thrust equation. So obviously, in most of the cases, we are using our nozzle to produce the thrust force, especially for our propulsion concern. Your nozzle is mainly for production of thrust. Okay, so your thrust is directly proportional to this portion. What is this? We call it as the momentum thrust, and m dot A into U, that is momentum drag, and this we call it as the pressure thrust. Okay, so now you see, if I'm going to operate my nozzle at correctly expanded case, you will have P by PA. This term P is equal to PA, that means this term will become 0. You will have complete thrust solely due to m dot A into 1 plus F UE minus UA. So all the thrust produced in your nozzle will be purely of momentum thrust. Okay. Now you could ask, so anyway, since it is in the plus term, what happens if I'm going to under expanded case? Means you could think that the magnitude of your thrust would be more, but that is not the case. What is the term we are having here? That is the pressure. So if there is a excessive amount of pressure is there, means what does that mean? We haven't converted our all the pressure energy into kinetic energy. So if this term is increasing, means this term will come down. So ultimately, when you add this together, it won't be greater than this term alone. So that is when you have the maximum thrust is that if your thrust is solely due to momentum alone, not due to the pressure. If you're having a pressure term, okay, it will be still less than the thrust produced during your correctly expanded case. Obviously, we need to produce as much as thrust is possible, right? So if I want to operate my nozzle efficiently, it should be operated under correctly expanded case. That's why we are studying what happens if you are having under expanded condition and what happens if you are having a over expanded condition. Okay. Now we already stated that during your under expanded case, your exit pressure is greater than your back pressure. So what does that mean? You are having still a certain amount of pressure which can be converted into kinetic energy. And one more thing is that anything in nature will try to attain the equilibrium, right? So what will happen is that here you will have P is greater than, since P is greater than PA, what will happen is that you have to reduce this PA to that so that it will be equal to that of your atmospheric pressure. So what will happen in the supersonic flow, as I already mentioned, the change of state will always occur through a wave. We have two types of wave. One is a compression wave, another one is the expansion wave. Okay, expansion wave is basically, as your name suggests, flow will be expanded. So what will happen during your expansion? Your pressure will be reduced, right? So here also we need to reduce our pressure so that it can attain equilibrium with your surrounding. So what you have to do is that, or what will happen is that you will have the expansion fan formation at the exit of your nozzle during your under expanded operation. So that's what. During your under expanded condition, your PE will be greater than PA. There is going to be an expansion fan will be forming at the lip of your nozzle. So why it is forming? To reduce your pressure so that it can attain equilibrium with your surrounding. Okay, this is what we call it as the under expanded nozzle or under expanded operating condition. Now, we have one more condition that is correctly expanded. I already told you. For the Mach number 2 nozzle, let's say, if I'm going to give 7.82 times, P naught is 7.82 times of my PB, what will happen? All the pressure energy will be converted into kinetic energy. At the exit, you will have P is equal to PA. So what will happen is that there won't be any shock wave or expansion wave is forming at the nozzle exit. Why? Because already it is having in equilibrium with your surrounding. So there is no need to either increase or decrease your pressure. So there won't be any compression wave or expansion wave will be forming. You will have something called a Mach wave will be forming. Basically, Mach wave is an isentropic wave. You won't have any change across this Mach wave. Okay, this is the correctly expanded case. This is what we want for our nozzle so that I can have the maximum thrust generation. Okay, now what if my P naught is less than 7.82 times of PB? Let's say same nozzle which is designed for M is equal to 2 we take. Okay, this nozzle is capable of expanding 7.82 times of PB. Instead of giving 7.82, let's say I'm going to give 5 times of PB means what will happen is that your nozzle will at somewhere inside your divergence section itself, you will have P will be equal to that pressure at that location will be equal to back pressure, but still your area is increasing. What will happen is that your flow will be continue to be expanded. So because of this expansion, what will happen? By the time it reaches your throat location, your P is going to be less than your back pressure. Okay, P is less than back pressure. This is what we call it as the overexpanded nozzle. Okay, so during this overexpanded nozzle, what will happen is that you will have the formation of a compression wave forming at the nozzle exit. Why compression wave? Because since your exit pressure is less than your back pressure, for the flow to attain the equilibrium, your flow pressure has to be increased. How your flow pressure has to be increased or how your flow pressure will be increased is that if it is passing through a compression wave, as your name suggests, your compression wave, when the flow is passing through a compression wave, your pressure will be increased. Okay, so you will have the formation of an oblique shock wave or compression wave at the nozzle exit. Okay, now what is the consequence of this overexpanded nozzle is that once again we have F is equal to m dot A into 1 plus F UE minus UA plus AE into P minus PA. So what is happening here during your overexpanded case, your P is less than your PA, that means this term will become negative. So even though you are having more expansion in your nozzle exit, but because of this negative term, once again the thrust generated will be less than the thrust produced during your ideal operating condition. Ideal operating condition means basically it is the design condition. Okay, so once again we can't operate our nozzle at overexpanded case. So now we could ask why we are operating, since we know what is the pressure for which you will have the correctly expanded case. Why can't I keep the same pressure to the inlet of my nozzle so that I can always have the correctly expanded cases? Because for example, you take your earth atmosphere, as you go higher and higher altitude, your back pressure is going to change. Okay, even though your P naught is not changing, your back pressure is changing. So obviously, you can't have a nozzle, okay, which is always producing a correctly expanded condition. So for that, how do we overcome under? We are going to see in the later section. Okay, so these are the operating conditions of our convergent divergent nozzle. Okay, so for your convergent nozzle, we have two operating conditions. One is under expanded case, another one is the correctly expanded case. Both subsonic flow generation as well as sonic flow generation at M is at P naught is equal to 1.893 times of PB. All of them comes under the category of correctly expanded case. Okay, that time you won't have any wave formation, and if your P naught is greater than 1.89 times of PB, for your convergent nozzle, you will have the under expanded case. Okay, so you don't have something called over expanded case for your convergent nozzle. So over expanded case is only applicable for a convergent divergent nozzle. So convergent divergent nozzle, we have three operating conditions: correctly expanded case, under expanded case, and over expanded case. Okay, so during your correctly expanded case, what we'll have? We'll have the Mach wave generation at the nozzle exit. Your P is equal to PA. You will have the maximum thrust generation. Okay. Whereas during your under expanded case, okay, what will happen if you are giving a P naught greater than its capability, you will have the under expanded case. You will have exit pressure is greater than your back pressure. To reduce your exit pressure, you will have the formation of expansion fan at the nozzle exit. Okay. And during your over expanded case, once again, your exit pressure will be less than your back pressure. To compensate for that, you will have the formation of oblique shock wave at the nozzle exit. Okay. So these are all the operating conditions. Now comes the question. So, do we have only problem with the thrust generation alone? Do we have any other problem because of the wave formation at the nozzle exit? Is that yes? Okay. Let's say this is the over-expanded case. Okay, so we have already seen during your over-expansion, we will have the formation of an oblique shock wave at the nozzle exit. Okay, because of this under-expanded or over-expanded condition, what will happen is that you will have the formation of shock cell or diamond shock cells at the nozzle exit. This diamond shock cell pattern will result in a huge IR radiation. Okay, say for example, where we'll have the supersonic nozzle, mainly for our fighter aircrafts, right? So for fighter aircraft, you need a stealth capability. If you're having a very huge shock cell pattern, what will happen is that your enemy will be able to easily trace your aircraft path. Okay, how does the shock cell form is forming? We have seen just only at the nozzle exit only, we have either compression wave or expansion wave is forming. How does this compression wave or expansion wave is continue to go and form the shock cell pattern? That's what we are going to see in this section. Okay, so we have let's take a over-expanded case. For the over-expanded case, I said your PE is less than your PA. So to compensate for that, you will have the formation of oblique shock wave. Okay, so what will happen is that here your flow is crossing this oblique shock wave. Here your flow is crossing your oblique shock wave. Your pressure will be increased. Your pressure also will be increased. But at the center location, what happens is that you have the crossing of or intersection of two shock cells, or two shock wave originating from the opposite corner of your nozzle lip. So what will happen is that since your flow is crossing two shock waves, the pressure raised here will be more than required or more than need. Okay, that is say initially let's say my atmospheric pressure is 101325 Pascal. My pressure is that, let's say it is some 50,000 Pascal. Now, let's say when the shock wave is forming, my pressure is increased to 101325 here. Here also 101325 here. But here what will happen is that instead of 101325, let's say 11325 like that, your pressure will be increased. That depends on the strength of your shock wave. So what happens? Your pressure becomes more than your required value. So what should happen? Your pressure has to be decreased. Okay. So, and one more thing is that we have something called reflection of your waves. One is a like reflection, another one is the unlike reflection. What is this like reflection and unlike reflection is that if the shock wave is hitting on a solid boundary, it will be reflected back as a shock wave only. That is, our expansion wave is hitting on a solid boundary, it will be reflected back as a expansion fan. That's what we call it as the like reflection. What is this unlike reflection is that if the shock wave is hitting a fluid boundary, it will be reflected back as the expansion wave. Expansion wave will be reflected back as a shock wave. This we call it as the unlike reflection. Okay, so here, what is happening is that the shock wave originating from here will be reflected back as a expansion fan. Okay, so because of this expansion fan formation, what will happen? Here, when the flow is crossing, what will happen? Your pressure will be once again decreased because we have excessive pressure. So it will be decreased. But at the center, we have two expansion waves are crossing. So because of that, expansion will be more. Once again, your pressure will be reduced less than your required need. So what will happen? Once again, this expansion band will be reflected back as an oblique shock wave. Like this, the continuous formation of this, okay, compression wave, expansion wave, compression wave, expansion wave will continue to form till the pressure of your flow becomes equal to your atmospheric pressure or surrounding pressure. Till that point, you will have the formation of this shock cell pattern. Okay, so what is that we need here? If it is going to be delayed, means what will happen? You will have a very long shock cells. Say, for example, here you can see in this figure you have this 1, 2, 3, 4, 5, 6, 7, almost 8, 9 shock cells are there. The shock cell length is very, very high. You see, almost it is equal to half of the length of your aircraft. So this much amount of shock cell is coming means, okay, one is you will have the infrared radiation, another which will be making enemies to detect your aircraft easily. Another thing is that this shock wave formation will contribute to the noise generated in your supersonic aircraft. One of the major noise source in your fighter aircraft is that jet flow coming up. Okay. So in the jet flow also we have two noise. One is due to turbulence, another one is due to this shock wave generation. Why? First of all, the shock wave is generated because of the different operating condition. Either it will be under expanded or over expanded condition. During the correctly expanded case, you won't have the shock cell formation. So it is very, very important to understand the operating condition so that we can control or we can introduce the mechanism so that we can increase the mixing of your flow comes out of your nozzle with the surroundings. So I can have a lesser amount of shock cell. Lesser amount of shock cell means, what does that mean? You will have the less noise generated in this case. That's why it is important to know the operating conditions of our nozzle. Okay. So with this, I'll end this lecture.
Like, share and subscribe. Hit the bell icon for more updates.